Okay. You want to start on the region?
Hi, welcome to LinkedIn. My name is Rachel Sanders. I'm a staff engineer, and on behalf of LinkedIn, I want to thank you all. Thank you so much for coming. A couple of things. We've hosted Bay Piggies and stuff coming up here. I was just asking, and it's been about 6 months, so they are hosted here monthly, and we're really happy to host them. And we're also really happy to have this talk here because Python, for those of you, for those of you who don't know, Python is our internal stack here at LinkedIn. Like all of our internal tools are written in it. I myself write in Python all day, every day. And as an aside, if you have any questions about how we do that, feel free to come and ask me after the talk. If I don't know, I can certainly redirect you to someone who does know. And I have been asked to tell you that we are hiring. So if you're interested in that, there are people downstairs who would love to talk to you. And I was also asked by my boss to tell you that we are hiring a contractor for my group. So if you're interested in that, let me know. So that, I also want to put in a plug for the group that I run, who also meets here at LinkedIn, which is Pi Ladies. So I run the Pi Ladies group. Some Pi Ladies now. And I really want to thank Guido and my extension, the Python Software Foundation, for being such awesome supporters of Pi Ladies over the last couple of years. And they are one of the major reasons that when I have new people coming into Pi Ladies, I can say, the Python community is one of the most welcoming and most awesome communities that there is. So, thank you very much. I really appreciate that. Okay, so that's all I had to say. So I'm going to turn it over to Glenn Jarvis, who runs the meetup group here.
All right. Thank you, Rachel. I just want to do a quick introduction. There are 3 groups here tonight, so I'd like to introduce you to each other. The first group, of course, is the one who helped us find our speaker for tonight. Speaker we're very, very proud of. It's the Bay Area Python Interest Group, the host for the evening. The second group is the group that really gets a lot of new faces coming in. It's the Bay Area Python, not Bay Area Python Interest Group, the Silicon Valley Python Meetup. 2 different names. And they get a lot of people that come in as well, so we really want to thank everyone who came in from that as well. And of course, the third group is LinkedIn themselves. Not only are they great hosts with lots of free food and beverages, but they also have a lot of employees who are here as well. So for those who are at LinkedIn, feel free to come to the Bay Area Python Interest Group or come to the Silicon Valley group, or quite often they're the same. So with all of that said, I would like to quickly introduce someone who really needs no introduction at all, the benevolent dictator for life, the person who's responsible for Python, Guido himself.
You guys hear me? Did I hear a no? Can you hear me now?
Yes.
Okay, thanks. Thanks for the great introduction and all that. It's great to be back. You guys moved around a few times and I lost track of where the meetings were. I found you again. My employer tells me that we're hiring. I'm passing that on. But I'm really here to talk about stuff I've worked on for more than a year now, probably about 15 months or so. And while it wasn't full-time, it felt like it's been almost the only thing I've worked on sort of for Python. Yeah, I've sort of helped some people break ties and sort of make tough decisions, but almost all my Python time has been devoted to Tulip, which got started, I think, in October 2012, when someone, I forget who it was, came up with a modest proposal of making some small improvements to a very ancient standard library module named asyncore, which was this really sort of poorly designed interface for doing select-based asynchronous I/O. It was started, I think it was written in the late 90s. It made it into the standard library at a time when I was not very sort of selective in what, whenever someone sent me new code, I was very excited that I had something new, especially if it had been tested out by more than 2 other people already. It got frozen into a really bad state, and then everybody started monkey patching the hell out of it. which meant that we were sort of morally obligated to keep it completely unchanged in the standard library, because all that monkey patching would horribly break whenever we tried to make an improvement to that module. So when someone brought up, yeah, there are all of these things wrong with it, and the design doesn't work right, I sort of said, well, maybe we can do something better. And somehow I got roped into thinking about, well, what is asynchronous I/O? What is the right way to do it? And here we are with one of the largest pairs ever written for Python, and a very large new piece of software that is only available in Python 3.3 and above. Although, so what is asynchronous I/O? It's essentially a way to do multiple I/O thingies like reading or writing files, or usually network operations, which doing them in parallel because the network is so incredibly slow compared to everything else you can do. So while it's not purely about networking, it's mostly about networking, and it's sort of how the question is, how do you do this? And so there's an old answer that says you create multiple threads. Each thread can do I/O using a completely tried and true synchronous interface. You say read, and it blocks until your bytes are there. And the operating system takes care of sort of managing the different threads. And that's all great because you don't have to learn anything new except how to start a new thread. And then there are some other things, like it turns out you can't easily create 1,000 threads, or you can't create 1,000 threads every second and then kill them all after they've done 3 tiny things. So there are other approaches. And on Unix, the traditional approach is using select or one of its successors called poll or epoll or kq. There's probably a new one waiting in the wings already. But on Unix, the basic philosophy is always, I have this file descriptor, it corresponds to some source or sink of data, maybe perhaps both. And I would like to do something with that file, like accept a collection, or write some bytes, or read some bytes. I mean, do something with that file descriptor. It's usually a socket or a pipe. But if I just try to write, it might block. And I never want to block because there's always other things that I can also do, like other file descriptors that I've also got bytes to write to. So I only want to write my bytes to file descriptors that actually have buffer space to accept at least 1 byte. And so in Unix, the way to do that is tell me when this file descriptor is ready to accept I/O of a certain type. And the certain type is really only it's either reading or writing. And you can say, well, here's a whole set of file descriptors. Tell me whenever any one of them is ready, or whichever ones are ready right at the moment, or within a certain timeout. On the other hand, there is a completely different paradigm, which is more popular on Windows, and I think also on mainframes, if anyone can still remember those systems, where you actually say, well, I want to do some I/O. Let's say I want to read some bytes from a socket. Here's my buffer. It's 10 kilobytes long. This is the buffer. This is the file descriptor. Start that I/O, but don't sort of block me. Just tell me when the I/O is done. And I get a callback in that case because there's always a function pointer there that gets called when the I/O is done. And the contract here is completely different. The contract is not, when I wake you up, you might try to write some bytes and it's probably going to work or read. No, it says when I wake you up, the deed is done. The bytes are in your buffer, or the bytes have been transferred from your buffer to the kernel space. What happens after that is really none of this API's business. But nevertheless, it's very different. It's sort of, in Unix, there's this optimistic approach. I might be able to write when it tells me that I can, while on Windows, there is this sort of completely different paradigm where you say, this is what I want to do, and tell me when it's done. And these paradigms are very different, and it's very easy to say, oh, I'm never going to be writing this kind of code on Windows. I'm only interested in this machine that's right here in front of me. But if you're writing libraries, sooner or later you're going to have to port that library. Probably someone else is going to have to port that library to a different platform, and that's where sort of abstracting all this away from the particular platform-specific way of doing it is important. So before I go on, I want to say something about threads. And there are different sort of approaches to threads. The sort of the classic operating system level threads that are nowadays at least present in all languages and all operating systems. They're pretty heavyweight. They're a very solid abstraction. Of course, we have things like locking and deadlocks and what have you, but sort of in terms of how what the guaranteed semantics are, what the operating system promises you is a very high guarantee of how it works. Which includes that it can switch between threads at any point in time, between any two instructions on some hardware, perhaps even in the middle of certain types of instructions. There's also significant cost, which sort of is the reason that you can't easily consider creating 1,000 threads for doing very small things and then tearing them down again. You have to create thread pools or some kind of queues. Sort of you got to. Basically, it's easy to have a server that handles 10,000 incoming connections, say, but it's not easy to have 10,000 threads, one thread per connection. So you have to do some kind of select or overlapping based approach. So operating system threads are actually pretty good unless you want to use many file descriptors or unless you have some kind of allergy for threads, which also occurs. I mean, some people just say they don't want to use threads for philosophical or ethical reasons. There's an alternative which sometimes is called green threads, which is, or sometimes micro threads. Stackless Python is also something in this space. There's eventlet, where an abstraction very similar to OS threads is implemented in user space in a more efficient way, which makes it much cheaper. You can actually have micro threads. You can have easily 10,000 micro threads if you can have 10,000 open file descriptors, say in Stackless or eventlet. However, the abstraction is not quite as solid. There are certain points where you cannot switch, so the application actually has to be aware of the fact that it's running in a micro thread, because if you're just sitting there in a while loop doing nothing but calculations, no other micro thread will run, even if all their I/O is ready, because the library is not going to give the CPU to another micro thread until the current micro thread says yield or lock or potentially wait for some I/O. So it has different behavior. And the interesting thing is, underneath micro threads, when they're used for I/O, is usually some kind of event. And that is where I want to go, and where I did go with Tulip, with that 3156 number, which I have thoroughly memorized, of course. So there is a unification, and it took me a while to sort of get to the right unification. When I first started thinking about this, I thought, like many other people who have written somewhat successful libraries for this, including that original asyncore thing, the standard library, that all the world is Unix style select. And maybe there are some different system calls that are more efficient, but they essentially work the same way. Well, little did I know, fortunately, Glyph, where are you? There it is. Somehow he butted into the discussion and educated me about many things, including transports and protocols, which eventually I adopted as one of the lower level layers of Tulip. Transports and protocols, and I'll get to what they are in much more detail later. But they are an abstraction that, even though it's pretty low level, it's still much higher level than either select or IOCP, which is that Windows overlapped I/O thing. And as an abstraction, it actually works pretty well because it's neutral about whether you say do the I/O and then tell me when it's done, or tell me when I can do I/O and then I will do it. Of course, underneath is still an event loop. There's also something I call tasks or coroutines, and I'll get more into that too because I have sort of a certain opinion about what the right, or what sort of most of the time the best way is to write code that handles I/O. And actually, I like code that is more or less synchronous. So deep in my heart, maybe I want to go back to those OS threads or maybe even real threads. But I have sort of objections to those ideas as well. So I came up with something in Python. Actually, I didn't come up with it myself completely, based on the yield statement. Again, we'll get to that. A little bit about sort of, eventually I sort of settled on a bunch of goals for the project. And I wanted to do really good asynchronous I/O in the standard library that was good enough that most people would actually be able to use it and would be willing to use it, and sort of just good enough so that it would actually be used, and people wouldn't feel the need to monkey patch the hell out of it, nor the sort of the desire to write their own library completely from scratch, but they might build on top of this. You know, practicality beats purity. I want this to be a good library. I want it to sort of still be used 5 and 10 years from now, but I don't necessarily want it to be perfect today. So I set myself some limits, and one of the limits was, well, it's got to work on Python 3.3, and it's got to sort of be released as part of Python 3.4, and that's that sort of, because those release schedules are pretty fixed. Although we lapsed the 3.4 release cycle a little bit. That sort of, the fact that I had a clear deadline, well, beta 1 is done, and I sort of got to be feature complete if there are some tiny things that we still have to tweak afterwards. That really helped me sort of limit the scope of the project. Another thing was that there was this brilliant new feature in Python 3.3 called yield from, which I really wanted to use for this. So 3.3 was the sort of the earliest version of Python that I was aiming for. And I thought, well, 3.3 for most people is already so far in the future. So many people are still using 2.6, 2.7. If they're ready to switch to Python 3, they're probably going to switch to 3.3 because that's the current best, most stable version. I don't want to sort of tell them, well, if you want to use Tulip, you'll have to wait even longer to 3.4 because in addition to that feature, that is a gating feature that's only in 3.3, we're also going to depend on some extra new standard I/O, standard library modules, and some extensions and this and that. So no new language features, even though at various points people have said, well, there's this particular thing with yield from that it's an ugly set of keywords. It should really be called await or whatever. Yeah, but that would require, I mean, new language keyword word in Python is a really big deal in terms of release policy. So that was all. We have to do it with yield from. Then another very important goal was something about interoperability with legacy frameworks, because while on the one hand, I wanted to sort of give people who want to do asynchronous I/O a way to do it using just the standard library, I didn't necessarily want to solve every problem. And there are many sort of frameworks, for example, Twisted, Tornado, a couple that I don't even know the names of, that or that I forget, that sort of have useful features or useful sublibraries or useful community that they don't want to kill off or compete with or anything. So it would be really nice if, for example, if Python's standard event loop mechanism was somehow, say, through some kind of adapter, interoperable with the twisted event loop, which happens to be called reactor. And I think that we've actually reached that goal. So that doesn't mean that I'm sort of wholeheartedly adopt any other framework's complete paradigm or set of APIs or philosophies. So if you know Twisted, you'll recognize certain things in Tulip, and you'll also find that certain things are very different. You might think, well, Twisted is clearly better, and I probably could explain to you why better is not always right for the standard library. But nevertheless, there is this interoperability at the level of the event loop, where many people have written event loops. There's like a whole slew of event loops written in C, for example, for multiple languages. They started out with libevent, there's libevent2, there's libev, there's libuv. There's a couple of variations of those things. Those are names I did not make up. Event loops are clearly a sort of a useful concept. And there are clearly different ideas about what the ideal event loop API is, but at the same time there are a lot of things that all these things have in common. Sort of everything is based on callbacks. You can schedule things to happen as soon as possible or at a certain point in the future. You can have things scheduled, triggered by I/O operations, and there are sort of timers and things. And beyond that, it differs. Some systems have this philosophy that whenever you want to do something, you create a new event loop, which is the child of another event loop. Other systems have the completely opposite philosophy, which is there is only one event loop, and all I/O shall use that one event loop and go through there. Tulip mostly uses that latter philosophy because it seems the lowest common denominator philosophy. But in any case, the idea is, and I really think that I've made this possible, is that different frameworks can actually live together in the same program, sharing an event loop object. And they may each have a shim on top of that event loop object that gives it the API that they're familiar with. And maybe that means that the names of the method to schedule callbacks are different, or the way you talk about I/O objects is different, the way you measure times is different. But nevertheless, in the end, everything comes back to this one event loop object. And this also means that using the event loop as sort of the switching point, you can actually have parts of your application written using one paradigm framework and another part of your application written using a different framework or paradigm. And they will certainly interoperate in the sense that the I/O will be multiplexed nicely and smoothly between the different parts. And they can probably even, with a little bit of additional adaptation, code in one framework can wait for something that is implemented in a different framework and return, sort of they can return values and send values back and forth. And there's sort of smooth interoperability at that point. Nevertheless, maybe one framework uses bare callbacks, another framework uses something like twisted deferreds, and another part of the framework uses Tulip's native approach, which is coroutines. Coroutines and tasks and futures. So, as I said, there were things that I decided I didn't necessarily want to wait for perfection or every possible feature. I don't want to sort of put the other solutions out of business. I just want to replace their lowest level implementation with something that can be shared, that can evolve sort of separately. I don't want to sort of, even though Tulip itself, in the undername async.io, is in the standard library, there are no actual sort of protocol implementations like HTTP or SMTP or what have you. None of those protocol implementations, though all of those could be written using Tulip, they haven't been written yet for the most part, or they haven't been sort of accepted well enough. Like, there are several HTTP implementations, but none of them are particularly better than others, so I'm not accepting any of those in the standard library. Another big non-goal was support all the Python versions. However, I'm sure there are some people who know what I'm hinting at there. But I do want I want to support a wide variety of systems. There's like Unix and Windows, and I always have to a certain twisted version of Unix. Different IP protocols, IPv4 and IPv6 should be supported sort of equally well. There are things to be done there yet, but for the most part, it works very well, whether you're using IPv6 or IPv4. It supports TCP and UDP as well as subprocesses and pipes and those other things. It's not completely platform independent, by the way. There are certain things that only work on certain platforms. And that is, again, sort of according to Python's pragmatic philosophy about platform support. Things you can do on every platform, there should be a standardized API. Things that only sort of make sense on certain platforms should not be ruled out just by the fact that you have a cross-platform API. And I also, again, I'm very grateful to Blyth for sort of pushing me in the right direction here. I wanted to build reasonably good support for SSL, and that's sort of, if you're a real security nut, reasonably good SSL support is a joke. But unfortunately, really good SSL support requires probably proprietary libraries, platform-specific libraries, a lot of stuff that I can't possibly all put in the standard library. Certainly not in the first release. So I'm hoping that Python's SSL, or I should really say TLS, support will eventually improve over time, and Tulip will automatically participate in those improvements. But sort of right now, if you give it if you say open an SSL connection, it will do its best to make that a fairly secure connection, and it will check that the host name in the certificate actually matches the host name you specified, and a few other things. And not every sort of Python standard library function does other. And so that is still much better than ignoring SSL and saying, well, if you want to use SSL, you're going to have to use the other way of doing it through the standard library, which is even less secure. Or it's so much more work that you're probably going to say, oh, as long as that web server also supports plain HTTP, I'm not even going to bother with SSL, which is, of course, the worst security decision you can make at all. Some more goals. So I already mentioned no new standard library modules, with the exception of the IOCP support for Windows, which was a completely different thing. But no new Python features. Also, no third-party software dependencies. That sort of was one of the constraints that made me rule out doing the absolute best possible job for SSL. I think over time, people will sort of build third-party solutions for SSL that will replace the built-in SSL support, but will sort of use the same interface so that you don't actually have to sort of you don't have to care about which implementation exactly is used, just how you get an instance. Finally, even though for me the most natural way to write code that handles network I/O is usually writing something that looks more or less synchronous and uses yield from for all the blocking points. I don't want to force that paradigm on everyone else, and especially I don't want to force that on the people who are going to write the interoperability layers for other frameworks. So at the lowest level in Tulip, it's actually all callbacks. That's what the event loop knows about. On the other hand, I don't force you to use callbacks for everything either. I'm not sort of, they're sort of very basic callbacks, and there's actually an intentional restriction. You can, whenever you specify a callback, you can usually also pass some arguments for that callback, which saves you a lot of lambdas. And those have to be positional key arguments. If you want to specify keyword arguments, you still have to use a lambda or functional tools or partial or something. Because that's more work, and I actually want to keep that the keyword space, namespace, open for different kinds of options. Anyway, let's see if I can say a bit more about the architecture. So Tulip really has three large components that are, well, I can't say they're independent, but they're certainly sort of, they live at different levels. They're different conceptual things. One part is coroutines and futures and tasks. And that's all about providing an alternative for either callbacks or threads or microthreads so that you can actually write your application code that sort of says, go do some I/O, and then waits for it to be done, and somehow then takes up where it left off and says, and now that the I/O is done, I can do something else, like a computation based on what I just read, or produce some more data and write some more data to the socket. The second major component is the event loop. And that is sort of the focal point for interoperability with other frameworks. There's also something called the event loop policy, which has to do with a separate API for actually setting the event loop object. And the final thing is transports and protocols. And that is the stuff that sort of defines the interface, the sort of mid-level abstraction for talking about I/O. Sort of writing stuff using a socket, but you don't actually have a socket, you don't use send. You have a transport object, and you use write. For reading, you have a protocol object, and with the transport, you'll call your methods on your protocol object. I'll explain a little more about that in a minute. But let's first talk a bit about those coroutines and related stuff. So a coroutine is really just a generator function. However, you have to decorate it with @coroutine, or it's actually usually you'll write @asyncio.coroutine if you just import the asyncio top-level package, which I actually recommend. But in example code, I always write just @coroutine. So the generator function represents some logic in your application, and whenever you do some I/O that might block, you use a yield from followed by some call that looks remarkably like a synchronous I/O call, like a receive or a read line or a write, or something like that. Then the second important concept is a future. A future is not code. A future is an object that represents the eventual appearance of a result. And how that result is produced, where that result comes from, is actually not the future's business. There is some other magic way that the future gets its result, and sometimes it's a coroutine that waits until something happens and then tells the future, here is your result, and then some other coroutine might be waiting for that future. It's also possible that the value of the result of the future gets set by a callback that's called directly from the event loop. The interesting thing is that the future treats results and errors more or less the same. An error is just a result that when you try to retrieve it, it actually gets raised. And this gives you a very neat, simple paradigm for handling errors, because it's just a try-except statement like you already know. You ask for the result. When instead of a result, the future has an error, then the act of asking for the future's result will raise that an exception that represents the error. If you catch that, that's great. Now you can sort of inspect the error. If you don't catch it, it will just bubble up to your caller and all the way back to sort of the root of your application. Finally, there is a task, which is actually a direct subclass of future that wraps a coroutine. And the task represents a result that is computed by a coroutine. The coroutine does some blocking operations, and then eventually it ends with a return statement that returns a value. Whenever that coroutine returns, when it yields, that just means sort of it waits for I/O and then it resumes execution. When it returns, it's really done. When it returns, the value of the future, that is the task, will get set. And again, when the coroutine, while it's doing all its stuff, somehow encounters an error, whether that's a name error or division by 0 or some I/O fails or whatever it is, that error will just be sort of temporarily stored on the task object as this is the error result, the exception of this task. And then whoever is waiting for that task, for that future's result, when they get woken up and they ask for the future's result, they will get that exception based on that. And then if that is another coroutine and they don't handle it, the same thing happens there. The coroutine terminates by erasing an exception, which then becomes that coroutine's tasks error. And so the errors gets bubbled up until someone actually handles it. And the way you handle them is, again, the standard Python try except statement. Although if you have a future and you really don't want to use a try except statement, there's also a separate method call you can use to ask it, well, do you happen to have an exception instead of a result? And it'll tell you yes or no. Okay, so here is a little bit of an example. I hope you can read that. I think that should be fine. Let's say we have a very simple HTTP client. It connects to a host and a certain port. And so let me see if I can get my laser pointer to work. Here we have open connection, and I don't specify that, and it's actually it's supposed to be just another user-written coroutine that somehow opens a connection, and once it actually has a connection, it returns a reader and a writer object. But opening a network connection is itself a blocking operation because you have to do a DNS lookup, you have to wait for the server to sort of actually acknowledge the request. It could also fail if there's nothing listening at that server, or if the host is down and the name cannot be found. And that would all be represented as an exception happening at this point. But suppose that the connection actually succeeds, then open connection actually returns a tuple of a reader and a writer. The writer has a write method, and this is actually an exception to what I just said. The write method does not block, it just buffers the data. There is a separate mechanism at a higher level in the library where if you are writing an unbounded amount of data and you're worried that maybe the network can't keep up and your buffer will grow without bounds, you can say, well, wait a minute, tell me when the buffer gets too full, and you can also specify what the definition is of too full, and then another thing, tell me when the buffer has drained enough so that I can start writing more. But if you if it's something like this, that all is completely a waste of time because this will fit in any buffer I can imagine. And that's all I'm going to write here. Now that's barely a valid HTTP request, bear with me. But suppose that we have a sort of a friendly neighborhood server that actually gives a response. What we're doing here, we're just reading lines, and again, r.readLine is a method on this reader object that is itself a coroutine. And so we must call it using yield from. So the yield from suspends this whole stack frame, the whole entire fetch coroutine, until the read line thing actually has a result, which could be, well, it could already be in the buffer, and then it actually doesn't block at all. It just returns immediately, but it could also have to wait for a whole bunch of TCP slowness before it finally has a whole line of data. So it may block. But once it actually has a value, this yield from returns, the value of the yield from expression is then the return value of the read line. So that's just a string, maybe an empty string. Now here what we do, because it's HTTP, we just decode it using Latin 1, which turns bytes into strings, and we strip them. And well, because otherwise the example wouldn't fit on the screen, and not actually parsing the headers or anything, and just skipping lines until I find the blank one, which is a sort of a 90% approximation of how HTTP responses have been parsed. And then I read the rest. And here I'm just reading until, this reads until the connection is closed. If the connection gets closed sort of forcefully, if the other side suddenly says disconnect, this will actually raise an exception. But if the other side sort of sends a nice, this is the last byte of my data, it will stop reading, and sort of once it's all done, it gives you the entire body as a byte stream. And finally, the return value of this generated fetch is going to be the byte stream. Now here is another coroutine that's using this one. So again, we say yield from something that will block for a while and then eventually return something. And so here we actually pass parameters to fetch, which will then open a connection to Python or port 80. Block, it's sort of, the interesting thing is here is a single yield from, but it actually represents many separate blocking operations. There's this blocking operation, there is one or two or many blocking operations in this loop until we finally hit that line point, and then there's this yield from. So control actually flows back and forth between the scheduler and through start to fetch to open connection and to the reader. And finally, when fetch hits this return statement, this yield from returns that data, and so data is the same value as the return value here. And then we print it to standard output and the programs. Now, how does start get called? There's a couple more lines that you'll have to look up in the examples directory in Tulip. So, unfortunately, I can't actually explain in finite time how this works. I tried thinking about it. I lay awake one night this week thinking, oh my gosh, there's got to be a way that if I draw enough diagrams of stack frames and back pointers and this and that, I can actually make everyone in the audience understand how coroutines pass control to each other. And I realized that it would be like 20 slides, and I couldn't possibly draw that many slides. I hate drawing on a computer anyway. But I also realized that it's actually not important to know how it works. All you have to do is squint and pretend that yield from isn't even there. And all these things are blocking I/O operations. And then you know what it does. And so you can read in PEP 380 the official standard definition of what yield from does, which is like a page of pseudocode with all sorts of intricate details about how exceptions get bounced into the nested generators and then come out again, and what happens when you close it. And none of that is important, actually. You just sort of look at this code, and now you look again. And that's it. That's how I understand the first version. So that was my back button. For those people online who have to click through it themselves. Okay, we're going forward again. So that's it. This is how you understand it. So I think that was probably the most exciting part of the talk. But wait, there's way more. So futures are something I did not invent. Far from it. Futures were introduced in Python by a previous PEP. I think that became active in Python 3.2. But those futures, the futures from that PEP, work with big-time OS-level threads. They are tied to a thread pool. Now, there's also a process pool, but even when you're using them with a process pool, there's still a thread operation, and there's thread-level locking. So those futures are not exactly what we want for Tulip, because in Tulip, we don't want OS threads and their locking and all that comes with them. But the interface of a future is very nice and elegant and sort of understandable. And even though you didn't actually see any futures in that example code, futures were used internally inside readline and read and open connection, and possibly even sort of in the parts of the code that you see, there might be futures there, but you never actually use their API directly because the yield from takes care of it. However, there are situations where you want to use a future, and the interface is simple. A future is either not yet, either it doesn't have a result yet, or it does have a result. When it has a result, it is called done, and it's actually either a result or an error. So there's this Boolean inquiry that says f.done, and it's either true or false. It's true when there is a result. Once there is a result or an error, it will never change. You can't sort of replace the result of a future with something else. You can't move that future back to the sort of incomplete state. It's sort of, it's in one state, and then it moves to one of two other states, actually three. It has a result, or it has an error, and it can also be canceled, which is kind of special. So to set the result, you call setResult with a value. To ask for the result, you call f.result, which will raise if there actually was an exception. It will also raise when the future isn't done yet. But when it's not, if you ask for the result when it's not done yet, you have a logic error in your program. You should have been waiting for it first. And waiting for it is not done directly through the future interface. You can't ask future.wait. You can say yield from future, and then yield from doesn't actually care whether it gets a coroutine or a future. Sort of, it does very different things, but the result is exactly the same. You block until there is a result or an error. And that's actually done, that's implemented for futures by adding callbacks to the future. So you can add one or more callbacks to a future. And what happens is when the future transitions from not done to done, all the callbacks will be called. And there's even a defined order in which they're called. And that is how the scheduler implements coroutines in waiting for futures. It registers a callback that wakes up the coroutine. And finally, there's cancellation. That's a very complex topic that I don't really have time to go into. However, as I mentioned, futures sort of are a very nice substitute for coroutines in certain cases. And in fact, many of the APIs in Tulip are defined to return something that is either a future or a coroutine. Of course, a future can also be a task. But nevertheless, there is a real difference. When you call a coroutine, the object you get is just a Python generator object. Well, when you call something that returns a future, the object you get is a future object, which is an instance of a specific class. It's the yield from statements that sort of unifies the two concepts into waiting until there's either a result or an error. But anyway, somehow you can create a future, then through unspecified means arrange for that future to eventually get a result. And then you use yield from that future inside your current generator, inside your current coroutine, I should say. And this will just suspend your coroutine until that future becomes done. Now, in practice, the way the APIs are designed, you almost never actually say create a future and then do something that arranges for that future to eventually get the result. What you do is you call some function, and that function could be called open connection, or read line, or read, or send, or write, or drain, or whatever. And that function will either be a coroutine or return a future. In many cases, it actually returns a future because that's how the implementation sort of can handle I/O, because the I/O is done by callbacks based on select or KQ or something like that. But sort of from the caller's perspective, you don't care whether what you get is a future or a coroutine, because you wait for the result in exactly the same way using the new syntax. So that is how futures and coroutines are interchangeable, or almost interchangeable, I should say. Because you can't set a callback on a callback. So a task, well, task is really this very mysterious thing. You know, that was actually Churchill about Russia. Riddle wrapped inside a mystery inside England. But a task is a coroutine wrapped in a future. And I actually already explained all that. Class task is just a subclass of class future. These are actual classes that are the different modules in the async I/O package. And the code is not even that complex. Certainly not that many lines. So a task also works with yield from, because it's just a future. From yield from's perspective, there's no difference between a task and a future. They have exactly the same API. It's the mechanism that gives the task the result that is different. So the typical way you instantiate a task is actually by calling a coroutine. And so instead of waiting for the coroutine, which would wait for the coroutine's result and so on, that call itself doesn't block. It's the yield from that blocks. Some coroutine call immediately returns and gives you a built-in generator object. You pass that generator object to the task constructor also immediately returns, but in the meantime, it has registered itself with the event loop and the scheduler, so that when you finally yield the current coroutine to the scheduler, that task will start running, and other tasks that have been created will also start running. In fact, well, of course, actually only one task runs at a time, or one coroutine runs at a time, or one callback runs at a time. But since each of those only runs for a very brief time and then it hits another blocking point like yield from, or a callback just sort of finishes, all of these things sort of get set in motion and start being mixed up very sort of in arbitrary patterns steered by the I/O. So when to use a task and when to use a coroutine. The difference is that the task actually registers itself with the event loop. And when you yield waiting for something else, all tasks that sort of exist and aren't blocked have an opportunity to run. Now there's still the matter of who runs first, and there's a very simple scheduler at the moment. The first one that became ready to run will run first, and then the one after that. But then everybody gets a chance to run. On the other hand, when you use a bare coroutine, something that was just a generator function decorated with @coroutine, if you don't yield from that particular coroutine will not make any progress, because there's no task that sort of links it to the event loop in the scheduler. So if you want something to happen in the background, will you continue doing stuff in the foreground, which could include blocking for I/O that you're sort of actively interested in? You also want something else to happen in the background, you use a task. If the thing that you want to do may take a while, but that's the only thing you're waiting for, it's good enough to use the bare coroutine. Now the nice thing here is that And this was the selling point of PEP3A, this all Greg Ewing's invention, mostly his. The big selling point is that with the original concept of generators in Python, it was difficult to take an existing complex generator and refactor it into smaller sub-generators. Because at every point where you want to invoke a sub-generator, you had to sort of iterate over all the values yielded by that sub-generator and yield them out of the current code. So sort of, if you have 3 lines of code that you somehow want to refactor into a separate helper function, subroutine, whatever, you have to replace them by at least 2 lines of code that call that thing, and then in a loop iterate over pull all the results out, and then push them out of your current stack frame. Yield from is just a short, in first approximation, is just a shortcut for that for loop that says for x in my subroutine, yield x. You just say yield from subroutine. And then it has a couple of additional syntactic things, like yield from itself returns a value, which is the return value of the coroutine. That's where I get sort of mind-boggling. But the bottom line is that using yield from, it's much simpler to refactor complex code into multiple sort of smaller, simpler coroutines that each block waiting for a particular operation. Like I had that fetch thing. There were 3 very clearly distinguished stages. There was the open connection stage, the header reading stage, and the body reading stage. It would have been pretty easy actually to turn that into 3 separate coroutines. They would just have to say sort of something like yield from open connection. Well, that one already had. Then yield from read all the headers, and then yield from read body. That one actually also had. But I could easily have refactored out the while loop that parses the headers and actually parse them rather than throw them away. And that is the nice thing that yield from does. And you don't, if you're using it for that purpose, you don't have to use futures or tasks. You just use one coroutine, yields from another coroutine, yields from yet another coroutine. And because yield from is built into the Python virtual machine, the Python interpreter, that all executes very efficiently. It's just a transfer from one stack frame to another. So exception handling, I think I already said everything I wanted to say about exception handling. Basically, when you raise an exception, both the yield from statement and the future mechanism and the way tasks and coroutines are woven into each other, everything conspires to sort of maintain the nice behavior where you you have something that returns a result, and maybe it raises an exception instead of giving you a result, and you can handle that in a uniform way using try example. So again, that is another thing that sort of gets bubbled out, and that gets handled very cleanly by yield from. If you have a subroutine, a sub-generator that you invoke using yield from, any exceptions raised in the subroutine that aren't handled in the subroutine bubble out to the callings generator very cleanly. Just as it, you could inline it back, and the behavior would be completely the same, as long as this and that is both generated. So what else? Another Zen thing. What? Of course, it's always possible that you have an exception, but there's nothing that's actually asking for it. Where does the traceback go? Well, the first version of Tulip, the prototype, was very hard to debug because I didn't have a good solution for that. And I knew that I needed one. And it turned out to be not so easy, especially in Python 3.3, Python 3.4. Turned out there was an easier way. But eventually we managed, and we make it now so that if a task object or a future object, I think only a task object actually, if it gets garbage collected and it still has an exception set on it, we actually log that exception. And unless you have you have so many memory leaks in your application that your task doesn't even get garbage collected, then you have a different problem. But then you can probably hit Control-C and everything will be garbage collected, and wow, your traceback will appear. So that's still my method of last resort. The situation is much better than it was before, and it really is. It's pretty hard now to sort of have a bug in your program that gets mysteriously eaten by the code. I mean, yeah, you can do that in synchronous code too with a try except statement and a pass in the except one. Now there are certain things that we don't log. The most important thing we don't log is if you have a task and it returns successfully and nobody asks for the result, we don't actually care, because that's the same thing as calling a function and ignoring its results. That's not a problem. Coroutines are a different story. There is a separate debug mode that collectly is a little iffy. Finally, the event loop. Well, what about the event loop? It multiplexes different activities, and it has a lot of different sources of things that happen. You can tell the event loop, the next cycle through the event loop, call this function. Now, if you do that with 5 different functions, then they'll be called in turn, and every one is sort of a separate cycle through the event loop. But eventually, they will all be called, and they'll all be called before things that are sort of scheduled at a certain time. You can say 5 seconds or 5 milliseconds in the future, call this callback. Now, how would you say, call this thing every second? Well, actually, the thing itself has to say, once it's called, it has to say, well, call me again in a second. And at some point, we have a design for an API where you could just say, call this thing every second. And then we got into a war about, well, okay, so how exactly is 1 second defined? You count that 1 second sort of from the start of the call or from the end of the call. What if it raises an exception? And then, of course, the next thing that API designers do is they say, oh, we'll give it an extra option where you can specify whether you want the clock to round or this or that and what you want to do on errors. And I said, whoa, now it's becoming really complicated. Let's just not have a timer API at all, because it's really only 2 lines of code to implement most of the timers that you would want to have. And then by looking at the code, you can see what it does, and you can tell what deficiencies it has. But you know exactly whether that timer will get lost when an exception happens or not, because you can tell where it sets up itself to be called again. And if you're still not happy, you can write a helper routine that does this for you, which is also only 2 lines of code. So callbacks and timed callbacks. Then there's, of course, the reason the whole thing started, which is I/O callbacks, where you say, I have a file descriptor or maybe a file object, and it corresponds to something that has sort of asynchronous behavior. Like it can be a pipe or a socket, or in some systems it can be a pseudo TTY, master or slave. On Windows, it can be a named pipe. Unfortunately, on no system can be a disk file, because disk files are always ready according to selected friends. But you say you have a socket, that's the most common case. The event loop has a direct interface to say, well, when this socket is ready for I/O, call my callback here. And that is a callback that sort of is persistent. You don't have to set that one up for sort of being called repeatedly. If you are done with that file descriptor, you have to say, stop calling my callback, or here's a different callback, because it can only be 1 callback for reading and 1 callback for writing your files. Another source of events, at least on Unix, is signals. Then sort of an iffy thing is we do actually have to work with events at some point for some purposes. A common example would be a database driver that just was written in C using Python's sort of extension API and was written completely synchronously. Maybe it's thread safe, but it certainly doesn't have any interface for asynchronous I/O. if you want to interact with such a thing using Tulip, you can't just say, well, give me the file descriptor corresponding to that database object. What you have to do is you have to run the database object in a separate thread and then communicate with that thread, send messages there, and let the thread send messages back. And fortunately, that's actually not a big deal, and there are some special interfaces on the event loop that let you cleanly say, well, here's some code that I want to run in a separate thread, and it actually returns a future that gets its result when that function in a separate thread has finally been called and returns value. And again, it does it, I think, for exceptions. And it uses a thread pool, so that it's even somewhat efficient. Oh, another sort of what to me was surprising. It turns out that Python has this socket API to DNS lookups, which is completely synchronous, called getHeaderInfo. It's like the modern version of get host by name or get host by header. And getHeaderInfo is completely synchronous, and it may actually go out to the internet and do DNS queries until it finally knows what Python.org points to. And so even inside Tulip, there's a one place where it has to call getHeaderInfo because you say connect to Python.org. It has to look up that address. It doesn't want to suspend your whole event loop just to do that address lookup. So we delegate that address lookup to a separate thread so that other tasks and coroutines can still run in the event loop. So that's why we have a fairly mature interface for talking to threads. And then the event loop separately has APIs for talking to various, for creating connections. And I've already mentioned all the types of connections it can set up. It can set up a subprocess, or it can wrap a pipe and create all the usual network connections. So here's a couple of examples of the APIs. I already went over most of this. This is how you set up the I/O. Actually, you don't normally want to use these. This is where the transports and protocols come in. They replace these, but these are sort of for the select-based event loops. These are there underneath for the purpose of implementing the transports and protocols. The signals, the threads. Sorry, I should have memorized the slides so I would have known not to say all this before starting. Okay, there's some new stuff you can sort of. At some point, and usually that's only in the main part of your application, and that really should only be a few lines of code. You sort of create your event loop, then you run it, and there's also the possibility of stopping your event loop explicitly, which is a pretty dramatic event. You shouldn't sort of be starting and stopping your event loop a lot unless you're running unit tests. You want to create a separate event loop for every test that you can do. But in a normal application, you basically you create your event loop and you run it forever, and that's it. And maybe you have some way like responding to the signal to stop your event loop. That's it. There is also a separate ultimate interface, and again, that one is mostly interesting for unit tests where you run the loop until a certain future completes. And it actually returns that future's result or raises that future's exception. The only place to use this is in the main. Let's see, what else do we have? So often you have to ask for what's the current event loop. Now you could sort of make sure that all your objects have the current event loop as an instance variable, and when you create a new object, you pass that event loop object along. And that way, you would never have to call get event loop. And there's a certain sort of moral judgment about getting event loops that says that's the better way. But even though we actually rewrote all the unit tests for Tulip, or we modified all the unit tests to support that paradigm, there's not a single get event loop call necessary for most of the unit tests, except the ones that test get event loop. But nevertheless, if you don't want to hold yourself to such a high standard, you can just call get event loop and various APIs will also call get event loop as necessary to access the current event loop. And the current event loop is, in practice, there's always one event loop for the current thread. And if you want to have multiple event loops, one for each thread, you actually have to do some extra work because the sort of, apart from the main loop, an event loop doesn't automatically get created for a thread. So in practice, there's only one event loop, and it's associated with the main thread. And that's enough. So let's see, there's the event loop policy, which is all very boring stuff that you can read. And so then there's the transports and protocols, which is this sort of mid-level API that abstracts away exactly how the I/O is done. It doesn't quite go all the way to the level of using coroutines and tasks. A transport represents the sort of the lower level part, and the protocol represents the application part, and they call each other. But the relationship is, in a sense, very asymmetric. So the transport represents a connection, and there's sort of a default transport, which the full name is really sort of a bidirectional stream transport, which corresponds to TCP, or perhaps a pipe or a named pipe. Or it could be TCP wrapped in SSL. I should really go over all this and say TLS. The Python standard library module for using TLS is called SSL, so what can I do? But the sort of, whether your transport uses a pipe or a TCP socket or an SSL connection, its interface to the protocol is exactly the same. When the protocol wants to write some bytes, it calls transport.write with the bytes. There's a few other APIs. When the transport has data ready for the protocol, it calls protocol.data received. And there are a few others like EUF received. Now the interesting thing is that this stuff is so asymmetric that you're probably not going to implement a transport. But unless you can do everything with coroutines and tasks, you're probably going to implement a couple of protocol classes. Because you have to sort of, in order to be called by the transport, you have to have a protocol class. And the only predefined protocol classes are empty. They have like all the methods, and none of the methods do anything. So if you want anything to happen when you receive data, you have to subclass protocol and say def data received, and then your handler. And that's, in a sense, all callbacks. Now, how does the protocol and the transport get created? That's a separate thing. The interesting thing is that a protocol and a transport pair, for example, something that handles TCP, works almost the same on the server side as on the client side, because after all, the socket is asymmetric. After the initial handshake, A can send bytes to B just as easily as B can send bytes to A. And sort of once the connection is in motion, from the perspective of the network and the applications running on either side, there's really not much difference between the client and the server. They're just both IP addresses plus ports. And so, while when you initiate a connection, you do something very different. If you're clients, you say, create connection. You actually ask the event loop to create a connection. You give a whole bunch of parameters, one of which is actually the protocol class or a function that returns the protocol instance. And this will return a transport and a protocol once it's done. On the server, you say loop.createServer, and this sets up a serving loop that every time it starts accepting incoming connections, and every time an incoming connection is ready, it will create a new transport protocol pair representing just that incoming connection and handle it that way. So what you can also do is you can separately create, for example, an HTTP and an HTTPS server using the same protocol class, just a different transport class, and then you can have sort of the same code handle both incoming TCP and incoming SSL connections. So here is a sort of a truncated version of the interface of the protocol. These are all calls that the transport makes under certain conditions. And there's a very specific order. The first thing that the transport calls on the protocol is the connection is being made. And it says, and oh, by the way, this is the transport. Because the sort of the way they're created, neither of them knows about the other right from the start. The next call is probably data received, unless you get disconnected right away, because then you'll get the connection lost. Again, there's this sort of clean shutdown concept of TCP sockets, which corresponds to a call to EUF received. And there's a dirty sort of disconnect, where you don't actually know for sure whether that was sort of, there was some kind of network disconnect, or the server went down, or you don't know what happened, but you know that the connection is not going to give you any more bytes, and then connection got lost, gets called with an exception. On the other hand, if it was a clean shutdown, the connection gets lost with none. UDP protocols are a little different because it's not technically a connection, and whenever you receive a packet, there's not just the data, but there's also the address of the sender. There's no notion of EUF in the file, but the same idea applies. Pipes and subprocesses are actually very similar to the sort of the bidirectional stream protocols. On the other hand, the protocol that wants to write data to the connection, and again, it could be writing to a pipe or a socket or TLS connection. It calls methods on the transport, which I wouldn't call them callbacks. They're just methods. They're many, like you call them, they do something, they return. And so what you call is write, which you pass bytes object or byte array or memory view. We call write lines, which is sort of this historical accident for the function that takes a list or an interval of bytes objects. Then there's write EUF, which tells the transport do this clean close of the connection, tell the other side. So when you call write EUF on the transport, the EUF received of the transport on the other end of the connection will be called. Except for TLS, this doesn't work. So you have to do it a little differently, and you just have to close the connection. The write EUF and EUF received are, in a sense, optional. But for TCP sockets, they are used. UDP has similar things, but again, you have to specify the address when you write data and stuff. There's no EUF concept. Let's see what else. So, because write EUF is optional, there is an inquiry function. You can also do a close that is really sort of a hostile close. You can call abort, and then except connection closed will be called on the other side with an exception, representing some kind of IO. I don't know exactly what exception. I mean, it's not you're not necessarily talking to a Python process on the other side. So there's no notion of it's sort of going to send a specific exception. There is the sort of TCP level concept of clean versus not so clean. And then pragmatically, sometimes you just want to talk to you just want to get the damn socket and ask it for something that only a socket has, like a peer name or sock name or SSL context. And so there is a get extra info method on the transport that the protocol can call whenever it feels like, with a string that represents, well, what implementation dependent thing do you want? And if it doesn't implement that particular feature, like if it's a pipe and there's no sock name or socket to be had, or if it's TCP socket and there's no SSL contact, they'll just return none. You can leave if you have a small application, I just created this HTTPS connection. Now I'm going to ask what the peer certificate is or something like that to check it double extra good. You can do that using this. You don't have to completely break through the abstraction. So in a sense, it's a leaky abstraction. So then there's the complex concept of flow control, which has to do with what if everybody's buffers are full. And so if the protocol is feeling a little filled up, it can tell the transport to pause, and then eventually has to tell the transport to resume again. The pause basically tells the transport, well, stop listening for that socket. Basically, let the kernel sort of fill up its buffer, and eventually the kernel will tell the other side that it's not ready to accept any more packets, and will sort of start slowing down the TCP connection. There are layers and layers and layers of stuff in the networking world that sort of deal with that. And when the protocol has processed all the data, or most of the data, and it's ready to accept more, it calls resume on the transport. Now, you still have to yield to the event loop before that, before you'll ever get these callbacks. You can't just sit in a sort of infinite loop just doing other calculations. You actually have to yield to the event loop. So you're probably going to structure everything in the form of short callbacks or using coroutines. Oh, we should have struck that out because all this resume stuff has been implemented, but it's also being changed a little bit. Never mind. Read it in the pack. So the big question is, are transport and protocol methods, are they coroutines, especially those callbacks? Sometimes it would be handy that if they could be coroutines, but they're not. These are just plain callbacks. And I already said the transport methods are just plain methods. And this is so that if you're implementing an event loop, which is a very difficult task already because you have to sort of keep track of all these file descriptors and timers and lots of stuff. In theory, it could be a very difficult job. We don't want the event loop implementation also to have to worry about how exactly to run a coroutine or a task. So there is a way to open a connection and get things back that are handy to use in the coroutine world, but it's a helper library that's a submodule of the Tulip or the async I/O package. It's called streams. And just yesterday, I think we discovered that there wasn't actually much documentation about it. There were certain types of questions people kept asking on the forum were all answered by, you got to use the streams module. So we're fixing that. So there is another open connection thing that returns a reader and a writer instead of a transport and a protocol. And readers and writers are well behaved when you call them from a coroutine. That's all I'm going to say about it. So I think I went over time. I apologize. But we can stay as long as people have questions. I do have a little bit of status update. Last time I talked, I think we were in the final stages of getting the PEP accepted and getting the code checked into the standard library. So the PEP has been accepted, although it's, well, provisional, which is a new sort of limbo status for PEPs that are sort of important, but the interfaces are so big that they need 1 or 2 releases to fully bake. So the expectation is that by the time Python 3.5 comes around, the interface will no longer change. I mean, after 3.5, the interface will no longer change in a backward incompatible way, but it's possible that 3.5 will have a slightly incompatible version of async I/O in the standard library. But the differences will only be noticeable if you're a very heavy async I/O user. That's the expectation. No absolute guarantees or promises, but that's the best we can do. We're just hoping for lots of feedback on this while Field 4 is out. So we did get it into the beta 1. It was closed, but we did get it in. There's also, for Python Field 3, you can get the whole thing from the cheese shop. We're We're still working out a few details. I mean, Victor, especially Victor Stinner, is very active at the moment. And he keeps finding small things in the API that are inconvenient or poorly thought out. So we're making small changes, but the changes are the typical kind of changes you would expect between data 2 and data 3. Spectacularly incompatible. And so 2 weeks ago, I sort of had some spare time, and I wrote an example program that crawls 1,400 HTML pages in 7 seconds using 100 micro tasks. And I thought that was pretty good. And new, you can actually use it on Python 2 as well. And this is Victor Stinner, and this is why Victor has been so busy. And this isn't a secret, but it hasn't been widely announced either. Victor is sort of very shy, and he announces this on the Tulip mailing list, where only like 10 Tulip developers are giving him feedback. So I thought I'd promote him a little bit. So we chose this brilliant name for the package. It had to start with a T, because the story why Tulip is called Tulip is that I realized that the 2 packages I was looking at most were Twisted and Tornado, both cool words that start with a T. So I wanted a cool word that starts with a T. And since, well, clearly not at the time of that I named Python, but since then I've been naming lots of things after obscure Dutch cultural references. So I thought that Tulip was a pretty cool name. The Troleus is actually also a plant. You can look it up on Wikipedia. It is an actual plant. And it starts with a T. So now before you all think, how is this possible? He didn't backward yield from. You actually, the code you write to use Troleus is syntactically slightly different than the code you write using async IO, using Tulip. So you say, in Tulip you say yield from coroutine. In Troleus you just say yield, because that's all there is. And so that means that the scheduler has to do more work, but your code looks mostly the same, and it actually runs pretty well. The other thing is, for various reasons in Python 2 and up to 3.2 actually, you could not return a value from a generator function. The generator could yield values, which are the values that the iterator that it implements produces. And it can return, but it can only return none. Because the idea was, well, after the iterator is exhausted, it raises stop iteration, and there's nothing else there to do. But that Cap 380, Greg Ewing sort of thought about it differently and realized that if you're using this yield from paradigm, you can actually assign a useful meaning to returning a value from generators. But because we had changed the syntax so that inside a generator you could not return a value in Python 2 and 3.2, you cannot say return X inside a generator. You will get a syntax error. So again, in Troleus, you can't return a value from a generator, which is the main way that coroutines in Tulip return values. So you have this somewhat inconvenient notation where you say raise, then this magical helper function return, and then whatever you wanted to return. And why is this a raise? Well, there's a long story. Look it up in the PEP. But there's a really good reason. He also had some problems with SSL, because it turns out that SSL context was a fairly new invention in Python 3. So he had to backport a bunch of that. He did all that, and I backported the crawler, which was mostly tweaking some of the imports, changing all the yields to yield froms to yield, and the returns to raise return, and removing a few places where I had sort of excitedly used all new fancy Python 3 syntax, like variable argument, tuple unpacking and stuff. And guess what? It actually worked. It actually ran just as fast because it's just even with 100 tasks in parallel, it's still IO bound. So that's the status. Questions? Oh yeah, for your entertainment, I have some links where you can find the path and the repo, the code.
If you want to set up the microphones, people on the stream can hear. That'd be great. So just go ahead and stuff.
At one point, you were talking about how coroutines were different than tasks. Is it possible that under the covers you could automatically treat every coroutine as a task?
It would be actually as simple as writing your own decorator that calls coroutine and then wraps the coroutine in a task. There's also a helper function named async that takes either a coroutine or a future and returns something that is always a future. You could do it yourself. I think that is essentially what Trollus does, actually.
Hi, you had these wonderful slides where you explained yield from and how it's very similar to some programming paradigms people might be familiar with. You said don't blink, right?
Yeah.
So my question is, what is the advantage of, since it's syntactically the same, the structure of the code is the same, just adding that extra word to every line, yield from, yield from, yield from? I mean, why don't you have, like, static int void thing, like, what's the advantage?
What's the gain of yield from?
Yeah, exactly. Just syntactically, not the rest of the thing, but just like what is the gain?
To me, I don't know how many people in the audience know C#. Okay, just for kicks, how many know Java? Okay. That confirms. That makes me win a bet ahead with calling this out. But in C# there is a feature that is you can map it keyword by keyword almost onto coroutines and yield from. Where here we write yield from, and in C# you write await. And here you decorate a function as a coroutine, and in C# you declare its type as async. So the terminology is different, but the concept is exactly the same. And what the C# compiler actually does is it enforces that the await statement or function, keyword, can only occur in functions whose type is async. And it generates different code for them that turns them essentially into coroutines. Now, why would you want that? Because there's no company that likes threads as much as Microsoft. So why would C# actually have this whole feature in the language that lets you avoid using threads and makes it explicit? I mean, here there's no type system that enforces this, but I still like, as the reader of the code, I like the fact that I can tell it's blocking this line. Oops. Here, I can tell it's blocking here. So I know open connection is a blocking call. This write is not blocking. This yield is blocking, but the rest is not. This yield from is blocking. And here, this yield from is also blocking. As the reader of the code, I like being able to tell that and sort of have that syntactically visible to me. Because it also means the way sort of the event loop and the scheduler and task and generators work is that when there's no yield from, I know that no other task will run. So from the moment I get this R and W variable out of this yield from, until I enter this yield from, I know that nothing can change the state of this R or W except stuff I call here. If you're using threads, on the other hand, if we have this version of the code in an OS level threads world, then I would have to sort of, at least in the general case, maybe not in this particular example much, but in the general case, I would have to worry about what if some other thread gets to run while I'm making this write call, or while I'm in the middle of decoding here.
Sure, but I was just talking syntactically the distinction between green threads and the yield front, rather than threading, which is like.
I was actually getting to that.
Oh, okay.
So, no, God, no, it's just kidding. I didn't expect you to still expect it. So the story why I don't like green threads very much is that sort of in a simple program using, say, stackless or gevent, it's easy enough to tell, oh, this is a call that yields to the scheduler because I see it. It's like yield. Well, it's not yield, but it's read or send or something. I know that's a blocking call, and here is a print, and I know that doesn't block because it's not doing socket I/O. And here is something else, and I know that. So what you do is you say, oh, I don't need explicit locking because between point A and point B, I don't make any calls that can yield to the scheduler, so no other microthread runs. So I can sort of mutate a whole bunch of global variables, or at least shared variables and shared objects. And as long as before I make the next blocking call, everything is nicely consistent again and the invariants are maintained, it doesn't matter that somewhere in the middle, while I was shifting things around, all the accounts didn't add up to 0 or something like that. However, what happens is that as your program using microthreads gets longer and longer, sort of you have this blocking call, you have this other blocking call, and then in between you have 10 lines of code that are helper functions. Now someone adds a log statement to one of the helper functions, and it turns out that for whatever reason you want to implement logging over network, and suddenly the log call actually yields to the scheduler, and someone else sees your messy invariant violated shared state. And then this is something that happened to me when I was at a young and impressionable age, and I've never forgotten it.
Okay, thank you.
So your focus here is on I/O, and specifically like network I/O. But another place you can see event loops a lot is in GUI libraries, like code for QTL use GUI libraries. And of course, if you're in a GUI context, being able to do network I/O without walking up the GUI thread is a really big deal. I'm curious if anyone has looked at integrating Tulip's events and coroutines and everything with any GUI systems anywhere.
I forget. I would look it up if I had my own laptop online here, because we have a small wiki page full of links to other projects that are using or starting to integrate with Tulip. It is not something that is currently sort of completely implemented, but it is certainly an idea I like very much. And I know that probably 8 months ago or so, for a while, I think around the last PyCon actually, I had a discussion with a couple of guys at Microsoft who were thinking about similar issues and gave me a whole bunch of useful feedback on Tulip. And their perspective was looking from the perspective of tablet GUIs, where they have some version of their system where all APIs have to be written in a completely asynchronous fashion. And so something like Tulip would be very useful for that. So I do hope that integration is going to be possible, and that's an area where probably sort of adapting the event loop to sort of live together with some other event loop, like system event loop or a GUI libraries event loop is going to be a useful feature.
So you said that a yield front can take a coroutine or a future. Can I implement my own class and implement a magic method and use like a class back to yield front as well?
I wouldn't recommend that. I think in practice you could only do it by subclassing the future class, because I believe there is an is-instance check in there somewhere. It's not really, you're not really meant to be doing that. That's sort of, you can write your own transports and protocols and event loops to your heart's content, but the coroutine task future side of the implementation is supposed to be sort of universal and work for everyone.
I think you have one more question. I'm happy to stay, but all the people I roped into doing the event would all like to go home. So.
All right. What do you think about the argument that in recent years there's been a lot of pushback about new stuff entering the standard library that isn't very well tested, well used as a module, and that if Tulip wasn't written by a core Python contributor, it would never be accepted without several years of use cases and usage behind it?
Yeah, I totally buy that. I stand behind it, and I have sort of, there's probably several Zen of Python items that are applicable, like now is better than ever, although right now may also not be the right thing. Practicality beats purity.
There's totally this unless you're Dutch.
Yeah. Well, that's why it's called Tulip.
Take bribes.
Too late. Okay, I think we're ready.
Yeah. Well, thank you so much for coming.
Hey, Rachel, we normally do announcements, and yeah, we're out of time. We'll just let it go today.
Sorry, I didn't mean to hijack your process there.
No worries, just normally
The guy was like, I don't want to go home.
Yeah,
I was like, all right, cool.
No, I appreciate that part. Very cool. We're not going to do it.